Welcome to Math 331. This is the little questions. This is going to be lecture 5. And so I want to talk very briefly about recurrences, not too much. If you have questions, please talk to me or the TAs. And then I want to start talking about inequalities. There are a couple of things that we have to do because this is supposed to prepare you for taking competitions, and you need to know certain inequalities. There are a tremendous number of inequalities. Which ones are useful? And how do you find them? How do you use them? A lot of the best advice, if you really care about doing well on competitions, is just do lots of problems. Look at a lot of your previous competitions and try to get a sense of which inequalities are used. And eventually you start to recognize that there's a natural subset of inequalities that you should try. Let me see if I can use this. Let me see if I can use this. Let me see if I can use this. How many of you remember taking derivatives? Is it possible for me to give a derivative that you can't do?
Yeah. Give us like a very abstract function.
If I give you anything with the standard functions and the standard, combinations, can I give you anything that you can't do? No. Can I give you something you don't want to do? Easily. You just keep hammering away with the different rules of differentiation. If I give you, f of x plus g of x, it's not that hard to say, probably a sum rule. If I give you, cosine of 3x cubed plus 7, what would be the first rule you would use? Chain rule. As soon as you hear the word of, you think chain rule. And eventually, you don't have to start going through your list. Is this a sum? Is this a product? When you see the of, you immediately jump to chain rule. The more familiarity you have, the faster you can reach that. In the days of AI, this is not a big deal. The computer will go through all the possibilities so quickly, it doesn't really matter. But when you're doing this on an exam, it's nice to know which ones to try. The more you do, the more sense you have of what you should try first. Similarly, when should I try to do something by induction? This should be one of your go-to techniques. It may not work, but it's a good thing to try. I will show at some point during the semester, I might be the first person to come up with this, a way to use L'Hopital's rule to prove, sums of powers of integers. It gets really bad really quickly, but in principle, it works. It's another way to attack a problem. For this particular problem, sums of powers of integers, it's much worse than induction, but it can be done. All right, so I don't want to go into too much detail. I will just, state it here for completeness. You were asked to read Appendix A of a paper that I wrote with some small students a couple of years ago. Here's the generalized Binet formula. And essentially it says if I have a linear recurrence of fixed depth, so the n plus first term is related to the n previous, and it's related by fixed constant multiples of the previous. So there's no products, the coefficients don't depend on n. Then we just guess as before that the nth term is r to the n. And we'll get a characteristic polynomial as before. And then it turns out by the fundamental theorem of algebra, there will be n roots, and you can write anything as a linear combination. The problem is if you have repeated roots. If you have repeated roots, it turns out you end up having not just lambda 1 to the n, lambda 2 to the n, but you could have a polynomial in n times roots. So the details are provided in the appendix. Again, if people are interested, I'm happy to go through and explain this, as well as give some intuition as to why you should have a polynomial, why that's the natural generalization if you have repeated roots. Okay. So I'll leave some blanks there in case we remember. So this slide is just a bunch of links, just so that everything is always readily accessible. The slides, as always, will be posted online. I just did a quick Google search of important competition inequalities. And here are 5 things that I found very quickly that looked somewhat useful. And then what I want to do today is I want to talk about some of the most important inequalities in mathematics and how you prove them. Anybody have any idea what the most important inequalities in mathematics? Again, you can make arguments for various ones, but this one has a lot of proponents as the most important. Any thoughts? So if x is a real number, then x squared is no negative. Turns out this is amazingly useful. Is this true for all numbers?
All real numbers.
All real numbers, yes. And that's why we say x is real. You know, if x is complex, I squared is -1. But any real number has a non-negative square. It turns out this is remarkably useful. Now, earlier in the semester, we were talking about some kind of weighted averages. And we said if, I think we were doing maybe probabilities or something. I forget exactly what it was. We had two people giving numbers.
It was to do with, we had Fibonacci's, like how we weighted.
How we weighted things. And we knew that when we were weighting things, it should be somewhere between the two people, right? If Alice believes it's 5 and Bob believes it's 10, what can you tell me about what they'll compromise on? Somewhere between 5 and 10. I only know of one instance where something like this has not happened. World War I think Churchill was in the Admiralty, and the British were very concerned about the rise of the German sea power. And for them, they viewed the German sea power as a luxury for Germany. For England, for Britain, it's not a luxury. They're an island nation. Parliament felt that they needed 4 dreadnoughts. Churchill felt that they needed 6. So they had a conversation and they compromised on 8. But after discussing, they go, you know what? It's a much graver situation than we thought. Okay. Why am I saying this? Well, the reason is I want to have a conversation of what properties should the mean of xy satisfy. And let's assume x, we'll do it this way. Let's assume 0 less than x less than or equal to y. So right now you're making a wish list. What kind of properties should the mean of x and y satisfy? Can somebody give me any property that if I'm giving you a function that's a mean, it should satisfy this property? Good. So one thing is we should have x less than equal to the mean of xy is less than equal to y. As a corollary, there's a really good choice of y that has a nice consequence. Yes?
0.
Well, we need 0 to be less than x less than equal to y. That's how I've normalized things. So give me a good choice of y as a function of x. So you want this to hold for all pairs x and y. This is a good choice of y as a function of x, where I want to apply this.
Y.
Yeah, y equals x. So if y equals x, this implies the mean of x and x equals x. Is that reasonable? Yes. If I'm taking the average of 2 numbers that are the same, I should get back that number. This is a reasonable property. I don't need this as a second assumption. This follows immediately. Are there any other assumptions you want, or is this all that we need for something to be a mean? That the mean should be somewhere between the two.
Just 2 numbers, then exactly halfway between.
Then well, if you do that, it's exactly halfway between, then that collapses the mean to one specific value. Then there's only one function that works, right? So you could say, if the mean of xy is halfway between x and y, then the mean of xy must be 1/2 x plus 1/2 y, or x plus y over 2. So I'm writing it as 1/2 x plus 1/2 y in a way that's hopefully illuminating.
What we want them to be like weight 1 x plus weight 2.
So one possibility is we could define the mean, and I'll call it p of xy, to equal px plus 1 minus py for 0 less than p less than 1. Or if you want, I'll even allow p to be 0 or 1. Now, will this always be between x and y? So as a nice exercise, prove that this is always going to be between x and y. Prove that this will satisfy your requirements. And again, the special case of 1/2, 1/2 is the one that you know. Where might you see a mean like this, where the things are not weighted equally?
Probabilistic weighting, or
But give me an example.
an expected value calculation.
Okay, give me an example of an expected value calculation.
You have a 10% chance of winning $100, a 90% chance of winning $200.
Good. So how much do you expect to win?
10% of. Wait, well,
And
I don't
then-
remember
so-
the numbers I said.
Right, exactly. So and that's why it's really nice that it's being recorded.
Yeah. I said, wait, what is 10% of 100?
Sure,
So-
whatever you said.
Okay.
And so you could use this to calculate how much you expect to win. You see stuff like this in classes. The final is worth this much, the midterm is worth this much, the homework is worth this much. What is your average? You see a lot of stuff like this in sports statistics. Not everything is weighted equally. Maybe you have 2-pointers and 3-pointers. So the ability to have unequal weighting is quite important. And so it's interesting to step back as to what is the fundamental object we're trying to study. We're trying to understand an average between two numbers, but there may be more than one way to do this. There's other ways to do this other than just adding the weighted numbers. Can anybody give me another approach? So instead of adding the numbers with weights, what could we do? We could multiply. So what if we looked at multiplying? What about multiplying? So if I just multiplied x times y, do you think that's going to be between x and y? What could I do to get that between?
X times y, square root of x.
So I could take the square root of that. And I could view this, if you want, as x to the 1/2, y to the 1/2, trying to write this in a illuminating way. Does anybody know what this is called?
Geometric.
This is the geometric mean. And what we had on the previous slide, this is the arithmetic mean. So can anybody think of how you might generalize the geometric mean?
X to the b times
Yeah.
y to the 1 minus
So-
b.
Is it more likely that you're going to see x to the p, y to the 1 minus p if I write it as x to the half, y to the half, versus writing it as the square root? This is where it would be wonderful to have two sections of this class and do this part of the lecture two different ways to see, are you primed now to see how to generalize this? Did it help seeing the previous problem where we put in the different weights? So you could consider more generally, could do maybe geometric mean p of x, y would equal x to the p, y to the 1 minus p, 0 less than equal to p less than equal to 1. What is the natural question you might ask between the arithmetic mean and the geometric mean?
That's bigger.
Which one is bigger? And you're given that this is supposed to be electron inequalities, right? Very good question to ask. How might you build intuition? Yeah, take some values. So let's look at, I'll do a arithmetic mean of xy is x plus y over 2, and g mean of xy will be the square root of xy. And so now what we can do is we can do x, y, arithmetic mean, geometric mean. Anybody want to start giving me some values? Okay, why 4 and 9?
Because like we have a square root, so we have to like.
So 4, 9 is good. Now you're going to have not an integer when you do the arithmetic mean, but we can do math like that. So we could do 4, 9. The geometric mean is going to be the square root of 36, which is 6. The arithmetic mean is going to be 13 over 2, which is 6.5. What else could we try?
Professor, I think
Try
you forgot
1,
to
1.
share.
And if we try 1, 1, no, I never
Hello?
explicitly said this, but we should check, does the geometric, we talked, I think, briefly, but maybe not enough. Is the geometric mean going to be between x and y? So I'll leave that as an exercise for you to do the algebra and check and show that the square root of xy is always at least x, and it's always at most y.
0 and 1.
Okay, so if we do 0 and 1, so I've said x and y are strictly positive to be safe.
Okay, yeah.
Because if we do 0, the geometric mean always will be 0.
Yeah. Wouldn't it be like the more different two numbers, the more the arithmetic thing is greater than the geometric?
So let's take x to be 1, and let's take y to be n squared, where n is big. What is the arithmetic mean? Yeah, good. Approximately, it's approximately 1/2 n squared. And what's the geometric mean? N. So you can see the arithmetic mean is going to be much, much larger. Without loss of generality, we can often normalize things. And so, again, this is a class in problem solving in proof techniques. Can I adjust things? So without loss of generality, can I adjust so that x equals 1? So let's think about what we have. We have x plus y over 2 versus the square root of xy. So how would I adjust to get x to be 1? I would divide by x. So I go from the pair xy to the pair maybe ab, which is going to be x over x, y over x. Right? What does the arithmetic mean become now? So this is going to be, let's call t equal to y over x.
Professor, can you hear me?
So what would the arithmetic mean become now? So the arithmetic mean of 1 and t is going to just be 1 plus t over 2. The arithmetic mean of x and y was x plus y over 2. So if I pull out and x, that's then 1 plus y over x over 2, which is just x times the arithmetic mean of 1 and t. And this might be suggesting another property of the mean that we didn't say explicitly. If I rescale all of my objects by a factor of 5, what should that do to the arithmetic mean? Scale by 5. If I divide everything by 3, what should that do to my arithmetic mean? Divide by 3. We didn't explicitly say this before, right? But maybe this should be another property. Another property. The mean of Rx, Ry should equal maybe R times the mean of xy if R is greater than 0. Basically, the world should not care if I measure things in meters or feet or furlongs. So if I'm trying to decide how I want to define something like mean, I might want a property like this. And then you can check and see, do all of our functions satisfy this property? There are a lot of math competitions where they give you something like this. Consider all functions with the following property. Prove that the function must be the following. Sometimes on multiple choice exams, they give you, consider all the functions that have these properties. Which of the following statements are true? Have you ever seen problems like this? One of the best ways to do this is just choose 2 or 3 functions that have those properties. And if one of those statements fails for one of the functions you chose, then you know it can't be that. So rather than trying to prove everything, sometimes it's easier in special problems like that to just write down explicit functions. But this is something we missed. We did not have this earlier, right? That when we're deciding what we will consider to be a good mean function, we just said, we want the mean of x and y to be between x and y. You know, if I'm trying to find the average of 4 and 6, I shouldn't get 8. Apologies to Mr. Churchill, right? And if I rescale everything, if I start measuring my amount in feet rather than yards, it should not change where things are. So the arithmetic mean of 1 and t would just be 1 plus t over 2. All right, so to recap, we have xy goes to ab, which is 1t with t equals y over x. The arithmetic mean of 1 and t was 1 plus t over 2. What's the geometric mean of 1 and t? Square root of t. And here, remember, the arithmetic mean of x and y was just x times the arithmetic mean of 1 and t. What's the geometric mean of x and y? That's the square root of xy. That's the square root of x times y over x. That's just the same as x times the square root of y over x. So this is just going to be x times the geometric mean of 1 and t. Everybody comfortable with this? That the geometric mean of 1 and t is just x times the geometric mean of 1 and t. I'm basically just saying I've rescaled things. The whole point of this is whatever relationship the arithmetic mean of x and y versus the geometric mean of x and y is the same as the relationship between the arithmetic mean of 1 and t versus the geometric mean of 1 and t. Without loss of generality, x equals 1 and y equals t is greater than equal to 1. The whole point is that I can make a simplifying assumption if I want. Without loss of generality, if I want to, I can assume that x is 1 and then y is some number greater than 1. So when we're trying to gather data, I'm really looking at 1 plus t over 2 versus the square root of t. Everybody comfortable with this? So now it comes down to 1 plus t over 2, the arithmetic mean, versus the square root of t, the geometric mean. Which do you think is larger, and do you think it depends on t? And here, we know t is going to be greater than or equal to 1, because we've chosen y to be less than x. I've normalized it like this. So which do you think is larger, 1 plus t over 2 or the square root of t? Does it, yes?
I guess it would still be 1 plus t over 2.
Okay.
Just because like as t gets really, really big, like a big number over 2 is going to be greater than the square root of a big number, just because it has a higher exponent.
Good, good. So when t is large, t is much larger than the square root of t. But when t is small, you're dividing by 2.
Maybe there's like a wise type situation.
Yes.
T is greater than equal to 1.
Yeah.
So when t is 1, then they're even.
Okay, so the equal at t equals 1.
Yeah. And then after that, it's monotonically increasing.
So how would you show that's monotonically increasing?
Subtract 1 from the other side.
So there's lots of ways to solve this problem. So let's let f of t be 1 plus t over 2 minus the square root of t. I will risk doing this for 1 less than equal to t less than infinity. How do you determine where this function is largest?
Sorry, no, not allowed to start my head.
No, but that's all right. So tell me where you think I'm traveling my fastest. You ready?
You okay?
Well, I only have one section to do of this class, so it's not too bad. So it would have been nice if I had 2 sections earlier, but for this one, actually, it's my left hand that's sweating. That's okay. So it's not just the derivative. What else? You don't look just at critical points. What else do you have to look at?
Second derivative.
Nope.
Boundary.
Boundaries. You always have to remember it's not enough to just check the critical points. You check the critical points and the endpoints. So here we check the critical points. F prime of t equals 0, and we check the endpoints, which for us is just going to be t equals 1. So at t equals 1, f of 1 equals 0. What's f prime of t? That's going to be 1/2 minus 1/2 t to the negative 1/2. Where's the critical point? Did I do the derivative correctly?
T equals 1 possible.
So only critical point is at t equals 1. Note f prime of t is greater than 0 for t greater than 1, so the function is increasing. Right? So we know the function's increasing, right? So this implies 1 plus t over 2 minus the square root of t is greater than or equal to 0 and is equal to 0 only at t equals 1. So this gives us that the arithmetic mean is greater than the geometric mean, except when the two inputs are both the same, in which case they collapse to being the same. So this was a nice way to prove this using calculus. Okay. Everybody comfortable with this? This is tremendous overkill. You know, if there's a mosquito that's bothering you, we're not going to drop an atomic bomb, on Williamstown to get rid of the mosquito. It will work. The mosquito's gone. But that is far more than is needed. So let's prove it without calculus. AM is greater than or equal to GM without calculus. So we want to compare 1 plus t over 2 versus the square root of t. Let's let u equal the square root of t, just so that things look a little bit cleaner for you. So we would then have to compare 1 plus u squared over 2 versus u, or u squared minus 2u plus 1 versus 0. If I multiply by 2 and subtract. Anybody recognize the left-hand side? So this is just u minus 1 squared versus 0. As u is greater than or equal to 1, the left-hand side is non-negative and is positive if u is greater than 1. And notice now that we're using that inequality I mentioned was very useful earlier in the day. So this is another way to prove that the arithmetic mean is bigger than the geometric mean. And what's nice about this approach is we're not using calculus. Anything that's really important should have multiple ways of proving it. And,
when you're like going through this kind of comparison,
yes.
using the term versus like to
because I don't know which way to put the inequality sign. I don't know if the inequality goes the same way all the time, or if maybe the inequality switches depending on what things are. Now that I know the left-hand side is non-negative, I can now go upwards and fill things in. What you might often do is you might start off at the bottom, and you might start off with, for u greater than or equal to 1, u minus 1 squared is greater than or equal to 0, and then work backwards from there.
Right.
So once you know the answer, you go backwards.
Right. So if you're doing like, if you're going to actually write this as a proof or something, going backwards, like
going backwards is fine. And then when you do that, it hides how you got there. And people often, how did you think to do that? Well, we really argued this way. How many of you have taken an analysis class? If you take an analysis class, you might have seen a 3 epsilon proof where you show that something is less than 3 epsilon. If you have somebody who wants to show off, they adjust things throughout the proof so that it ends up less than epsilon. And they just have a sense of what things are coming so that they can choose things so that at the end of the day, it's less than epsilon. If you're trying to show something is less than epsilon, and in the end you show it's less than 3 epsilon or 17 epsilon, it's not a big deal. Let epsilon equal epsilon prime over 17. You just do a change like that, and then you're fine. So sometimes people just try to make things look a little bit nicer. Again, there's more than one way to prove this. We haven't done nearly enough proofs. Let's do another one. AM versus GM. And this will allow me to almost surely use results that you may have seen but have forgotten. What's the most important geometric formula? Not the quadratic equation, although it is related to squares. Pythagoras. So we know for a right triangle, a squared plus b squared equals c squared. So I have deliberately not looked at my notes for this problem. One of the things that I will say that's extremely important is we made the simplifying assumption without loss of generality that x equals 1 and y is t. That reduces us from a 2-dimensional problem to a 1-dimensional problem. I can't emphasize enough how valuable that is. when you did multivariable calculus, there are some problems that you can tweak down to a one-dimensional problem. And when you can do that, that's much nicer. So what I want to do now is use a result from geometry that hopefully you've seen, almost surely you've forgotten. I'm going to take a circle, and I want the diameter to equal 1 plus t. I believe that's how I want to do it. Let me think this is how I want to do it. Or do I want the radius to be? Let's see. I'll fix that in a second if I need to. So if I have that as t, let's see. Does anybody remember the theorem I'm trying to write down? All right, so let's call that R. I think I want that to be 1, and this can be R minus 1. So we'll keep that open for now. Does anybody see any other right triangles that I could add? And I'll put in some labels. A, B, C, D, E, F. Can anybody give me any more right triangles? CFD, good. And there's one more right triangle. I'm sorry? ACF. So ACF is a right triangle. And there's another right triangle that I got when I drew the line AF. AFD is a right triangle because AFD is a right angle up at F. What is the length of the line BF? BF is R. So we have a lot of right triangles. And now we need to introduce lengths. Do you want to make FD equal to A and AF equal to B? Do you want to do alpha and beta? I need letters. All right, let's do alpha and beta. So we'll do alpha here, we'll do beta over here. So can somebody give me relations involving Pythagoras? You got a bunch of right triangles. Start giving me things.
Alpha is t squared plus 1.
Okay, almost. Not alpha, but alpha squared is t squared plus 1. Good. Give me something else involving t squared.
T squared plus R squared plus minus 2R plus 1 is equal to R squared.
All right, so that's just R minus 1 squared equals R squared. What else do we have?
T squared plus in brackets 2R minus 1 squared.
What else do we have?
Alpha squared plus beta squared equals cancel with 4r squared.
It should be 4r squared, which is really just 2r squared. So if you look at what's going on, we can write alpha in terms of t and r. We can write beta in terms of t and r. So we should be able to get a relationship between t and r. Is there a relationship between r and t? If we want to have a circle, if I tell you t and I tell you that's 1, does that force the length r on me? Yeah. Once I give you 3 points, once I give you these 3 points, there is a unique circle that's going to go through those 3 points. So r is actually forced. So this is going to give me a relationship between r and t. And so you can use this, and you can actually get the arithmetic mean, geometric mean from this. So I will leave this, I have a handout that goes through and does all the details on this. I believe the relationship is if you have 2 chords intersecting where one chord goes through the center, then it's going to be, FC times CE is equal to DC times CA. I believe that's the relationship you have in geometry. I think it's FC, the length of FC times the length of CE is equal to the length of DC times the length of CA. I think that's what you get. And from that, I think you also get the arithmetic mean, geometric mean. So I'll leave that for you to play with. But again, the idea is we're starting off now with something well-known, the Pythagorean formula, and we're trying to find something geometric from this. Now, there's other things you can do with the mean. You could try to figure out what could the mean of 3 quantities be? What could the mean of 4 quantities be? What's the mean of the means? And there's a lot of games you can play. And so one of the things that I've linked to is a paper by 2 of my friends on just proving some generalizations of inequalities for means. So if I give you 0 less than x less than equal to y less than equal to z, what can you tell me about the mean of x, y, z? Can you give me anything that should be true about the mean of x, y, z?
Between x and z.
It should be between x and z. And so then the question becomes, what possibilities can you have? So the standard, the arithmetic mean is 1/3 x plus y plus z. I have to be a little bit careful here. I don't really care about these inequalities. I care about the thought process of how we would find them. We also have the geometric mean, which is going to be, what do you think the geometric mean should be of 3 quantities?
X, Y, Z to the power of n.
X, Y, Z to the 1/3. So then the question becomes, what else could we have? How can I view the first one? How can I view the third one? The second one, sorry, the second one. The first one I've got x plus y plus z. The second one I have x times y times z.
I think we do write it as like x to the power of 1/3 times y to the power of 1/3 times the power of 1/3.
You could do that.
But I'm not sure what you're getting at.
Right. And that's the whole point.
Oh.
Right? No, the whole point, no, this is the whole point. You have to try to figure out, how can I generalize? I'm giving you 2 data points. The first is x plus y plus z. The next is x, y, z. Now, I'm assuming x is less than equal to y less than equal to z. But if I didn't assume that they were ordered like this, what should the mean of 1, 2, 3 be versus the mean of 2, 3, 1? The same. What would you call a function like that where I can change the order of the variables?
It's commutative.
Not commutative.
Symmetric.
Symmetric. How many m's in symmetric?
2.
2, that's what I thought. It's a shame that the word symmetric is not symmetric, but. So we have x plus y plus z for the first. We have x times y times z for the last. Can you think of something else we might try? I want something that's symmetric. It's okay if it's not a mean. We can fix it later. Can you think of something I could try? What's between them? It's got to be symmetric.
Would it be like x times y times z to the power of 1/2?
X times y
Oh,
times.
yeah. Sorry. X times y times z to the power of 1/2.
Nope. The first one I have x plus y plus z. The last one I have x times y times z to the 1/3.
Like 2/3 minus.
So don't worry about the constants. Don't worry about. Give me how x, y, and z should be interacting with each other. Oh, I don't mind if it's complicated, but I want something that's symmetric.
Something like x over x plus y plus z plus. Sorry.
Yeah, we're out of the Commonwealth.
X
So.
over like y times z plus y over x times z.
Okay, so now what you're doing is you're starting to take products in twos. Look at the first one is I have the polynomial, the quantities in the polynomial to the first power. In the last, the quantities are to degree 3. I have 3 terms. What should the middle one be?
Something like 2.
Yeah, so look at maybe xy plus xz plus yz. Well, if I do it over x, y, z, then that's going to normalize things. So let me divide by b and raise it to the 8th power. Let's try something like that. So that gives me something where I have everything coming in degree 2. Now, we know, we'll call this, the mean A, B, X, Y, Z. We know if X equals Y equals Z, what should we get? So what should we get if X equals Y equals Z? We should just get X. So hopefully this will work. Good. So, whoops, I lost just a bit. So if X equals Y equals Z, we get X. That means 3x squared over B to the A has to equal X. Thus, B should be what? And A should be what? B should be 3, and A should be 1/2. So this is not a proof, but this suggests xy plus xz plus yz over 3 squared is a mean and is between the arithmetic mean and the geometric mean. So we'll do more about this in the next class on Wednesday. Again, my goal is to talk about the thought process and how did we find this to study. And again, a lot of this is, I kind of know where the answer is. Not surprising, I've done this longer than you've been alive. I want to try to write the extreme cases that we have, the arithmetic mean and the geometric mean, in such a way that I could ask, what else could I look at? And then you can start to ask, which one is better? For certain problems, sometimes one mean is better than another. For a lot of things, you care about the median income, if you do economics, versus the mean income, because 1 or 2 outliers can make a huge impact. And so there are relationships between all of these. What I really care about today is the thought process of how we get to stuff like this, trying to see how do we generalize. That's one of the most important skills you can learn in a math class. Take something that someone has done and push it further. All right, so this is a good place to stop. I will stick around for a few minutes if anybody has questions. And then I'm gonna just